Okay, welcome to the seminar series on cognitive robotics offered by the Queen Mary University of London. Today, I'm very happy we have Ildar Farkhatdinov from our very own Center for Advanced Robotics at Queen Mary, so an internal speaker today. And Ildar, so we have been knowing each other since we both joined Queen Mary more than 4 years ago now. And together, of course, after the lead of Professor Kaspar Althofer, we have created the Center for Advanced Robotics at Queen Mary, of which I think we are both very proud. And his research is in physical human-robot interaction. And I especially like the fact that in his present research and also in his past research, he has always taken inspiration from observing behaviors in humans and animals in order to create intelligent robotic systems. And although he may not call himself a researcher in cognitive robotics, I think these are the very things that are on which cognitive robotics is based on, right? Taking inspiration from biology to create intelligent systems that can be useful for people in real life. And in fact, many of the things Ildar has worked on have clear and direct applications to assisting humans in different situations. So I think this is quite remarkable. And yeah, so without further delays, I will leave the floor to Ildar to start his presentation. Thank you very much for being with us today.
Thank you, Lorenzo, and please let me know if there are any technical difficulties on the way. I have prepared about 40 slides today to discuss my previous and current research, and I'm happy to see in the audience my colleagues, collaborators, friends, and as well as the members of my team at Queen Mary. So thank you everyone for coming, and also thank you, Lorenzo, for organizing this seminar series for this module, which is also a very nice idea to introduce state-of-the-art research to our cognitive science robotics students. Okay, yeah, presentation today will be about human-robot interaction, and specifically how do we use sense of touch and motion in interaction. Here is my team. This picture is, this photo is now 2-year-old. Actually, team is slightly larger. We have 2 more PhD students, and 1 postdoc should be joining us sometime in summer. Our website is here, and the team, Human Augmentation and Directive Robotics team, are part of the Center for Advanced Robotics at Queen Mary. So our website is here, Queen Mary Robotics. My expertise, as well as our team members, are mechatronics, control, human-machine interaction, and more specifically, haptics. In our research, we take bio-inspired approach. So we look at humans, take expressions from human behaviors, motion studies, psychophysics. We design bio-inspired robots, and then we see how these robots can be useful to humans. For example, here, robots to assist human walking. And these are my key topics for the last 8 years. So haptics for teleoperation, robots to study humans, robotics and virtual reality, augmenting human balance, and assisting mobility. Here is an example of what I did for my PhD. It was back in France. Now, I looked into behavior in animals, for example, birds, and one specific feature they have is head stabilization, which enables them to achieve stable vision, as well as improve their body and space perception to better control their body. So we looked into how this can be useful for mobile robotics, robots which require walking, moving in 3-dimensional space. And we designed several control approaches for this. It was done together with Professor Anna Mikalaska from McGill University, Canada, Vincent Hayward from Sorbonne University, Paris, and Alain Berthoz from Collège de France, Paris. Now, Vincent Hayward and Alain Berthoz, they are both members of French Academy of Science. It was a nice time, and I learned a lot from about bio-inspired approaches and how we can learn from vestibular system and spatial perception. So today I'm going to talk about sense of touch and sense of motion, sense of space in different human-robot applications, and I will start from telerobotics. So sense of touch, one sec, okay. In humans, we have two major organs, human skin and human muscles, which provide us with a sense of tactile touch and sense of proprioception, how our body parts are oriented with respect to each other. So in our skin, we have lots of different receptors. They respond to different stimuli. It can be mechanical pressure, can be pain, can be vibration, can be temperature. And muscles, they not only produce action, they not only produce forces to move our body, they also have sensors, Golgi tendon organs, which can tell how much they stretch and how much effort they produce. So our body, our central neural system can control our limbs, upper limbs, lower limbs, knowing where they are. So these two major organs are important when we speak about haptic interfaces. And haptic interfaces, they are robotic systems which can render sense of touch. Nowadays, everyone has a portable haptic interface, at least majority of us. Smartphones, they have integrated vibration actuators. They can produce different haptic sensations. For example, when you type, you can feel a reaction from your phone vibration actuator as you were touching real buttons, but in fact you are touching a flat screen. More traditional haptic interfaces are basically robotic systems which can generate force feedback. In here you can see an operator or user manipulating virtual mechanical parts in virtual reality. And with the help of haptic feedback device, we can feel when these parts collide each other. This is important for virtual assembly tasks. So we are producing forces with the help of electrical actuators. In this specific example, there are 6 electric actuators which provide force and torque feedback. It's a Haption system developed by a French company, Haption. And more recently, virtual reality, wearables, other technologies enable us to have wearable integrated force feedback and tactile feedback. So like in these haptic gloves, for example. Okay, now force feedback can be very useful in telerobotics. With my colleagues back in South Korea and Russia, we did study mobile robot teleoperation, when we need to send a mobile robot to perform a remote task where humans cannot go, for example, cleaning nuclear facilities. So in this case, we can use cameras, like on this robot, but cameras are not always useful if we have difficult light conditions, if we have limited networking bandwidth channels. So we can introduce haptic feedback or force feedback. So we use the haptic interface, desktop haptic interface, which was communicating with a mobile robot. The interface was used as a joystick to send positional speed commands to a robot, and we were using force feedback functionality to feel the environment around the robot. So if there are obstacles around, we can render this information with the help of forces. We ran a small study when we asked users, human participants, to navigate a robot in a corridor without collisions. And the goal was to reach the final point as fast as possible and as accurate as possible. We compared scenarios without force feedback, with conventional force feedback, and with our specific custom designed force feedback law. Here you can see the results for conventional and for traditional, for proposed force feedback approach on the right. So clearly you can see the difference between two types of force feedback. Conventional approach had collisions. We can see the trajectories in space, while our approach had no collisions, because our approach has taken into account not only position of the robot with respect to the obstacles or the walls of the environment, but as well as velocity, relative velocity, how fast we approach the obstacles or the walls. As a result, we achieved smooth trajectory following, no collisions, and improved completion time. Currently, with my PhD student at Queen Mary, Joshua Brown, we're extending force feedback capabilities for mobile robot teleoperation, and we developed novel type of haptic interfaces. For example, here you can see a haptic interface based on particle jamming. So it is enclosed in a pressure-controlled environment. We can create vacuum, or we can create positive pressure if necessary. In addition to small particles, we add a vibration actuator, and by controlling the power of the actuator as well as the pressure in this cavity, we can modulate how the haptic or touch waves are propagating to the surface. Then a human will be able to touch this surface to feel what is actually happening with a remote vehicle. For example, when our vehicle is interacting with rigid objects of a remote environment. This interface is currently being integrated in computer-like joysticks so that we can test handheld interaction with a remote vehicle. As well as designing haptic interfaces, I have been working on designing robots or haptic interfaces for studying human sense of touch. And in particular, here I will talk about how can we use robotics to study human proprioception. One way to study human is to use functional magnetic resonance imaging with the help of robots. Functional magnetic resonance imaging uses large scanners, like you can see here, but these scanners are creating extremely strong magnetic fields. So anything metallic, for example, a metal chair, will be attracted to the bore of the machine with extremely high forces, so over 1,1200 kilograms here. Of course, if we have human aside, this will be the last time human is doing scanning. So we should not put anything metallic next to the scanners, otherwise we can kill patients or our participants. But robots are made of metals, metallic parts, so we should be careful how can we put robots next to the scanner. Our solution, together with the colleagues at Imperial College London, Etienne Bourdet, I was a postdoc in Etienne's team, when I was funded by European Union, and we developed a solution for studying wrist movement, wrist muscles, with the help of a cable-driven robotic system. So we put all electromagnetic components as far as we could from the scanner bore, more than 2 meters away. Then the magnetic forces were low enough, and we had cable-driven operation to study the effect of upper limb control. And we compared how our interface performs during scanning. So basically, we should compare the image of a human brain when the robot is there and when there is no robot. Robot is passive. Basically, we ask a human participant to perform the same wrist movement, flexion extension, with the robot and without. And we compared the pictures of the brain when the interface was off on the left, and interface was on the right. So we achieve pretty much same response. This is a sensory motor cortex, which is taking care of in this case, right wrist movement or right arm movement during our testing. And this interface was portable, so we could easily put it in a taxi and go to a hospital to do the experiments. It's important for fMRI robotics when you study human brain that the interface are easily mounted within the facility, because fMRI facilities are extremely expensive, and if we know from COVID crisis, CT, computer tomography, is these departments are very busy nowadays to do diagnosis. So we need to design robots which are easy and simple to mount. Final thing we did with colleagues at Imperial, together with Arash Arami and Xin Yun Huan, in the group of Etienne Bourdet, was a lower limb interface to study lower limb neuromotor control. Again, it's a cable driven, and we attach a harness to a leg of a human participant. An extremely powerful motor can create fast, rapid changes of the forces, which will cause our muscles to flex and extend at the hip level, knee level, or ankle level, depending where we fix the attachment. So now the robot was designed such that it is adjustable, so we can test different angles of the lower limb. We can test how our muscles behave at different leg orientations. And this was the first experimental measurement of hip joint stiffness, which we reported in literature recently. And the measurements, they correspond to estimated simulation models. Next, I will speak about how sense of motion and balance is important for human-robot interaction. Our vestibular system is responsible for sense of motion and balance. We have two organs located in the left and right inner ears. So each vestibular organ is composed of two subsystems, three semicircular canals. They are responsible to measure angular velocities of your head. And we have two otolith organs in each of the vestibular organs, which are responsible to measure the vector sum of gravitational and translational acceleration. So they are basically responding to head tilt when you are not accelerating. So when you stand still and you tilt your head, we can know how your head is tilted thanks to these organs. And these organs are also responsible for balancing. So balancing is an important function in our daily life, as well as it is important for humans. And here is a short video showing how we augment sense of balance in humans with the help of lower limb exoskeletons. It was a European project where I was part of when I was at Imperial College. It was funded by EU and called Balance. We designed new control methods to detect and augment human sense of balance. Okay, we used Lopez, lower limb exoskeleton developed at University of Twente, to test how can we design hip assistance, so hip abduction movement to move hip to the left or to the right during stepping, if we detect a perturbation or loss of balance in lateral direction. To do that, we applied hip assistance torque. So here you can see a plot. This is 1 second when perturbation was applied in orange, left or right perturbation. Our body moved in that direction, let's say by approximately 20-25 centimeters, center of mass, and our leg, left or right leg, has to move to do a stepping to the left or to the right to recover balance. So we assisted this movement with the help of custom designed assistance torque, and this torque was provided with the help of a wearable robot. We designed an experiment to explore long-term effects of this torque. So at first we had baseline walking with perturbations, so only perturbations and only human. Robot was passive, was not providing any assistance. After that, we had adaptation to robot assistance. So we introduced robot to the system, and we had same perturbations. They were left or right randomly distributed. And we wanted to see in 50 trials how will our central neural system, neuromuscular system, will adapt to that. At the end of this adaptation, we randomly removed assistance. So assistance was sometimes non-present, and human participant was not aware of that. So we wanted to see what happens after lots of assisted trials. What if robot is removed? This is a visual recording what happens without assistance and with assistance. It's hard to say anything. So we analyzed kinematics and muscle activation. So muscle activation for hip abduction for the left or right leg. You can pay attention here on the three colors. So blue is a hip abduction or hip angular movement when there was no perturbation. Oh, sorry, when there was a perturbation, but there was no assistance. So human was recovering balance on his or her own. Now in red, we have a case with assistance. So we can see increase in the angular motion of the hip movement. So that is what we should expect because we are giving extra force. And yellow is when assistance was randomly removed at the end. So we can see we coming back to the original level of kinematic behavior of the hip. So we remove assistance and we return to where we were before. Regarding EMG, the difference here is more notable. So in blue, we have no assistance, balance recovery without assistance, muscle activation. And when we apply assistance, we can see significant reduction in assistance in all participants. And at the end, when assistance was randomly disabled, we can see muscle activation comes to the original level of the blue level. So these were main achievements, and this was basically repeated for all participants. And at the end, we tried that similar protocol with a post-stroke survivor, a female patient going through a rehabilitation, 71-year-old, 2 months after stroke. Visual observations, they need to use hands to assist balance. So in healthy participants, hands were not required. Here, hands are important. But after all, EMG and kinematic results are very similar to adult subjects, of course, at a different scale, though. So this was a very nice time when I was at Imperial College, and it's funded by European Commission. Now, coming back to vestibular organ is very strongly integrated with other senses we have, so such as proprioception, hearing, vision, and brain uses this information in different ways. And in some cases, we have illusions which we can observe in our daily life. When you sit in a train, if you now travel, but many people don't travel, sit at home. But when you were sitting in train, which was still, train at rest, and train next to you was moving, your eyes could observe this motion, and you briefly had an illusion of self-motion illusion. So this is a typical self-motion illusion when we have a circular change of optical field on the left or on the right, then our body will feel that we are either translating or rotating. Of course, your brain will quickly realize that it is not you who are moving, but it will take maybe half second, maybe longer sometimes to understand that, because we receive information from haptics, from proprioception, from the chair. So brain will be tricked only in the beginning. But these solutions are very useful when we design a human-robot or human-machine interfaces. For example, in computer graphics, in computer games, this can be useful to create illusion of action when you move in space. Such as here, we have lots of particles looming to you, and your brain can feel, depending on your conditions, of course, and the size of the screen and your environment. Your brain may feel that you are moving. So we looked at it, how this can be used for virtual reality and combined with haptics. So whether we have a sensation of our body motion, if we provide visual stimuli, as well as feet vibration. So we were vibrating feet in accordance to the optical flow. And we found out that feet vibration can actually increase this illusion. This was done together with Vincent Hayward and Nizar Warti in Sorbonne University, Paris. Now, with my PhD student Francesco Soave, in collaboration with Nick Brian Kings and Lorenzo Picchinali from Imperial College, and Nick is from Queen Mary, we're developing a hardware prototype for embedded haptics in a chair, or wearable haptics for virtual reality self-motion illusion. So with potential applications in computer games. This is still work in progress, but this is very closely related to telerobotics and to spatial awareness when we have visual only information. Now, let me try to create a quick poll to ask you. Actually, I can't do a poll here, but I can ask those of you who feel this is that this is a picture moving down, raise your hand. And if you think this is picture moving up, do nothing. So do you think this is a view down? Then raise your hand. And this, if this is up, then don't raise your hand. And let's see. So I have about, let's say, 40 to 50% of people respond that this is moving down, and the other either not sure or think that it is moving up. In fact, this is moving down if we look carefully, but if we don't look carefully, if we don't have much time to make decisions like we often have in telerobotics, we need to have information about this coming through other senses or other abilities. So we can equip robots and human operators with interfaces to support this decision making. So, for example, if we have a robot moving upstairs, like we see on this picture left, four-legged robot, camera only view may not be enough, as we saw in this small test. So with my PhD student Atta Ottaran, we designed an ankle interface. You can see here a video on the left, which can be used to present this information about moving up and down. We can tilt the ankle platform with respect to the slope of the remote environment or the verticality sensation. So our robot can feel we are moving up and down with the help of inertial sensors, and we can tilt the platform accordingly. But what Atta did, he also introduced a functionality to use this interface as a walking input. So we can use foot tapping, like you see here, foot tapping. It doesn't play. To control a walking of a remote robot. This is a virtual reality demonstration of a bipedal system. So a human operator can use foot tapping on the left to control legs of a remote robot. And we can use upper limbs, because they are hands-free now, to control the upper limbs. So it is a full body embodiment, using lower limbs to do walking and using upper limbs to do arms control. And even though this is not really a walking interface in terms of not realistic walking, but we found out that users actually like this. It is very easy to learn, and our data shows that, I will show it a bit later, that it is, this interface can be efficiently used for walking. And final function I want to introduce for this interface is haptic feedback. So because we have actuation at the ankle level, we have a motor which we can program to represent different terrain models. So we can program dynamics of the terrain. For example, it can be a rigid object, rigid floor. It can be ice, so we can introduce cracking, like here. It will crack several times before we crack the full surface. And this is perceived by a human operator during walking very realistically, actually. Here you can see some of the data. So on the left, 3 plots of ankle platform angle at walking at different speeds, 5 km/h, 6 and 7. So what you see is the frequency of foot tapping is increasing. And this can be mapped into the avatar walking speed or avatar displacement if we simply take a time integral. We asked 11 participants to use the interface, and we observed how they stabilize the speed of walking. So we asked them to maintain certain speed. And at day 0, we introduced 10 trials. So after 5 trials, all participants, this is the data from 11 participants, were able to stabilize their walking speed. And next day, when we invited them again 2 hours later, they maintained pretty much same level. And 1 week later, when they came back to lab, they were able to use their skills. So there was a skill learning. It was not required for them to start from the initial trial, like the initial level of performance like they had in day 0. So this is a very nice performance indicator for the designed interface. What we plan in future is to look into full level of telerobotics embodiment for 4-legged robots or wheeled robots or bipedal robots. Now, haptic feedback, which I introduced in the beginning, can be also useful for spatial navigation to understand motion and the environment around us. And this is specifically useful for people with disabilities. For example, people who are deaf and blind at the same time. So they cannot see and they cannot hear. For them, touch, sensation of touch is crucial. And there are several types of tactile sign languages which are used to interact with them. Here is a small demonstration video of one of the tactile languages.
Coffee? Yes, thank you. How do you take it? Like it back. Good.
So this person on the video is deaf and blind, and the lady is using a tactile sign language to ask whether he wants coffee or tea. So now speech of deaf blind people is obviously affected, but as well as they have reduced mobility, they have problems in balancing and walking because of lack of vision. Sometimes the vestibular system is affected as well. And because of all these factors, they have reduced independence. They cannot do sports. They obviously cannot drive a car. But in fact, we found people who can ride a horse. In the UK, there is a charity, Riding for the Disabled Association. They introduce animal-based therapy for people who are deaf-blind or people who have other disabilities, or sensory or physical. Now, horse therapy is an important type of animal-based therapy which can improve self-confidence. It can improve psychological and well-being state of such people. But it is expensive because we need a horse rider and we need a tactile sign language interpreter. This charity came to us at Imperial College London when I was a postdoc there. And they also were introduced to us by a shadow robot company, Rich Walker. And together with Maciej Ogrink, we developed a wearable vibrotactile interface to be placed on the arms of a horse rider, and a smartphone application for instructing therapists, which was sending remotely wireless communication signals for left or right turning commands, as well as double command, both left and right at the same time, to stop. And we have tested this interface. So here how it looks like. We have tested this interface with several deaf-blind horse riders. So you can see conventional method on the left and our proposed therapy on the right. Here, what we observe is a completely independent, physically horse rider, deaf-blind, can command the horse. This is very important from a psychological point of view, because in that case, the rider has full control over the animal, and the instructor only intervenes when there are health and safety issues. For example, there is an obstacle in front. This has been now more than 5 years since this interface is being used, and it has been used at national horse riding competitions for people with disabilities. Finally, I have started a new project recently to use sense of touch, sense of motion, and vision to develop new supernumerary limbs for improved human ergonomics. So we are working with a group of collaborators and our team to develop super limbs to carry heavy loads. At the same time, these super limbs, robotic ones, they should be able to be safe, and they should be able to support our back and balance. So we are designing back support mechanism to maintain our posture healthy, as well as a robotic tail to improve balancing of the overall system. If one of you is interested, I have an opening postdoc position in this project. And here is the final slide, my contact details. Feel free to email me, as well as our websites where you can learn more about our center and team. Thank you very much.
Yeah, thank you, Ildar. I think it was very interesting. Okay, so I'll open the floor now to questions. I don't see question in the chat at the moment, but please feel free to type your questions, or you can also raise your hand and ask. I will start with one, Ildar, and I think maybe if you want, you can unshare your screen, because maybe we don't need it. Worst case, you can put it back up. So my question was about the system you showed with on which Joshua is working on, this haptic feedback with the granular jamming, in which basically the user has their own finger on this surface, and they can receive some haptic information. What is the information that you can actually convey there? Can the user understand something about the friction in the remote environment, or something else?
At the moment, it is an open question for us. Friction might be more difficult rather than softness and hardness or structure of the material. The problem I can see with the friction is because we use a rubber film on top, which has already quite a lot of friction itself without any actuation. Now, friction can be, and the interface is designed for the applications when there will be no sliding between the finger and the interface. So the finger will be in touch, and we can normally apply normal forces, no tangential interaction. Now, if one of the prototype we developed now has 2 vibration actuators inside, one on the left and one on the right. We have a hypothesis to be tested that if we independently modulate left and right actuators, we can create a sensation of sliding.
Okay.
But it is to be tested experimentally, and because sensory motor integration here will be crucial, we have, for example, if it is a telerobotics finger sliding across the surface for textile surface exploration, we should, and a human operator will be able to visually see that finger sliding on the surface, but while his or her finger will be stationary on the interface, but the interface will be creating that illusion.
Okay.
So
nice.
by modulating two actuators. So that can be where we can look into friction.
And you think in that case you can both give the illusion of sliding and at the same time give the feeling of the texture, or?
I believe so.
Okay, yeah, that's very interesting.
Texture plus also softness, hardness.
Okay. And yeah, okay, yeah, I mean, I think in general, I mean, I had a general comment on your talk. I think it's really nice how you presented that in so many cases, it's like a multimodal perception. And so the different senses, they contribute together. Senses and movements, they contribute together to create our sensations. And so, for example, in this specific example is both the actual sensing and the movement of the fingers, either real movements or like fictitious movements.
Exactly, and this is an important concept in cognitive robotics, action perception loop.
Yeah. Okay, so about feedback, so there is a question in the chat about haptic feedback in VR. To what extent of reality and precision it has? So I think it's a bit of a general question, but what is the level of haptic feedback that you can provide in VR? How realistic can it be?
Okay, existing commercial interfaces already can achieve quite a lot with the help of linear resonant actuators. So they are vibration coil type actuators, electromagnetic actuators. And when you play a game or you explore a virtual environment, for example, like in tactile exploration, you touch something, that is already quite realistic. The problem comes when you want to feel forces. Force feedback is expensive because it requires more advanced robotics technology. So forces is still are not used in wide applications. They are used in very specific professional applications. So vibration-wise, you can already do a lot, but thanks to the fact that our brain can combine vision and touch very well. And sound as well. Let's not forget about the sound. Sound, when you're scratching the surfaces without touching them, if you see somebody doing that, you can even already understand what is the surface made of without touching it. So sound is crucial as well. So VR, vision, sound, they are very well developed, and introducing haptics is helping that, of course, but we can achieve a lot with simple haptic interfaces now already.
Okay, yeah, thank you. And then there is a question, how is the foot tapping? I think this is related to Ata's work of the platform, working platform. How is the foot tapping synchronized with the correct leg of the robot?
Yeah, at the moment, it is not synchronized because our platform does not have a sensing capability to detect which leg is pushed. So now there is a plan to add additional sensor so we can know how to synchronize it then. But very often it is not necessary if a human operator does not see the avatar legs. So we see that we are moving, but we don't care if I moved just now with the left or right leg. That is not important. Or action of walking, which we generate with with our feet, is already quite strong enough to provide a sense of embodiment. Now, if we want to do something like kicking, when we use a specific leg to kick, or one leg will be stance, another leg will be swing leg. And in the applications when it is important, then we have to do some synchronization, but not at the moment.
Okay, and I have a related question on the same system that you showed before. You mentioned that you can also give haptic feedback with the platform because you can actuate it in a specific way. So in that case, the haptic feedback that you can give to the user, do you think it's possible for the user then to recognize different surfaces he's walking on or similar things?
Yes, we actually did a study which I didn't present. We asked participants to classify between simple virtual wall, like one spring damper system, two when we feel that we crack once and then the second level of surface cracking, and then multiple. And this was all possible to recognize within 70–80% success rate perceptually through psychophysics studies. So it is all fine, and we only played with the structure. We can do different level of stiffness. We didn't study that. We can introduce different level of viscosity or damping. That will be basically, if we are walking in a mud, it is easy to put your leg in the mud, but it is hard to remove it. Right. So that is to do in future. There is a lot of potential with this interface.
I see. Very interesting. There is a question in the chat. Hello, Fang, by the way. And the question is how to measure the balance of standing and walking, and how to determine the correct level of balance.
Hi, Fang. Hope you are fine. Thank you for coming to the talk. Now, how to measure balance of standing and walking. So basically, same principle as humans use. We rely on our vestibular organ, as well as tactile proprioception from legs, because we are standing on a assume we are standing on a rigid surfaces, so we can get information from that. So in that case, robots or exoskeletons can be equipped with inertial measurement units to detect sudden acceleration changes, as well as joint sensors, angular sensors, which can tell if our center of mass goes beyond the base of support. If our center of mass goes beyond the base of support, means we are losing balance now. Base of support is the area between the 2 feet we are standing on for human or for robot. Now, that is relevant to your second part of the question, how to determine the correct level of balance. There are different ways to measure balance. Some people call them stability index or stability performance indicator. One way is where we project the center of balance, center of mass of our body to the ground. If it is between our feet, we are fine, we are stable. If we are beyond, we are not stable. And the distance from the projection to the left or right border of the base of support, this is what can be used as a simplest possible measure for performance, for quality of balancing. There are other things which take into account velocity, center of pressure, but they are more advanced.
Okay, thank you. And I have, so there is a question in the chat, but I had a follow-up question on this system of the balancing. In the experiment you showed, if I understood correctly, you showed that your assistive system that basically is suggesting one side motion of the leg, so your assisting system was helping, and then when you removed it, the subjects were going back to their normal walking, but I was wondering whether instead that could be used also as a kind of rehab. So basically, whether if used for a certain number of times, then a subject can learn how to prevent, so how to improve their balancing even when they don't use the system.
Yeah, I agree with you. I did not mention that that specific experiment and project was firstly addressing healthy participants to augment existing function to the situations when the perturbations are too high, so that we need extra support. Now, for the case of rehabilitation, when we need to motivate a person to recover certain neuromuscular functionality, the controller should have been designed differently, and it should be using assist as a needed strategy.
Okay.
So we should look. We should basically have information about how active is a human himself or herself, how good are their muscles performing, and to support this activity through our control, not to overwrite it like we did it.
Okay, I got it. Okay, there is a question in the chat in regards to the haptic guidance system. Has there been extension to use said technology for wider navigation? For example, creating haptic GPS for visually impaired or deaf-blind people?
Yeah, this has been studied previously by different groups. I think over the last 20-25 years since mobile technologies appeared and haptics became less costly, people introduced belts, or they put hats where they put vibrators around their head to study this. Why we went into that specific project, because we found it interesting for two reasons. It was a deaf-blind person, so not much research is done in that case, and animal-based therapy is something which was novel for us. So in that specific application, there was novelty, but overall the topic itself, using vibration to tell where to go, wearable vibration, is not novel. So we didn't really look into wide applications because it was already there.
Okay, yeah, and I think so. The question was from Anastasia. I think if you are interested in that, you can look also at sensory substitution research, in which there is a lot done also with using different kind of stimuli to provide basically user who don't have a sensory perception because they are, for example, deaf or blind, or they miss that perception, to substitute that with a different kind of perception. And in this case, in the work Ildar is presented, this is haptics, but it can be sounds or it can be others. And basically you can, for example, substitute what you typically do with vision, do it with sound instead, etc. And there is indeed quite some research there that might be related. And I see another question in the chat. How would the supernumerary robotic limbs know how to assist the task the user is trying to achieve? Also, how could they determine what stage of the task the user is in?
So that's an open question to many robotics applications at the moment. So how to balance between manual and fully autonomous control. So I see there are three levels how assistive robot can behave. First is fully autonomous, when we have sensors attached to human, to robot, or maybe cameras, external sensors. And then a robot can get this information and decide, okay, I do this now, I do that now. And this is where artificial intelligence might be helpful. Second level is hybrid, when we can use some inputs from human. For example, human has a button to say that now I do task, load carrying task, now I do lifting task, and this button will activate these modes, and the rest, the steps in between, will be done by autonomous system. And the easiest level is probably fully manually controlled, like in Telerobotics, we fully control the robot. But in that case, if it is a super limb robot, the goal to assist human, but if human will be busy controlling the assistive robot, it's not really assistance, it's creating more task. So we should be careful with fully manual tasks. So short answer, we can use sensors to design a controller which can know what to do and when. But how to design it, there are many different approaches.
Yeah. And I agree, it's pretty much an open research question in many fields. Also, human-robot cooperation and shared control. These are very active topics of research at the moment. Okay, and there is a question by Marie-Luce. In VR, have you tested how much touch force feedback combined with vision or instead of vision improves object affordances? Or let's say, I guess, the perception of object, and how can object be used?
So I did not really do a specific study on that, I believe maybe there are studies which explore more specifically how well people perceive rigid objects with the help of haptic feedback in virtual reality, and how can they interact, for example, if they have a virtual tool in their hand, virtual hammer, and how can they operate that. So I did not really test this. In VR, my key interest at the moment is how to provide a sense of motion and sense of environment, spatial perception. So not specifically objects. I'm sorry that I'm not able to answer this, Mariluz.
Okay, and of course, if there are further comments, Mariluz, as much as anybody else, can also raise the hand and pose the question and then speak. I have another kind of general question. In most of the studies you presented for haptics, so in several of them you're using vibrations. In others, let's say, for example, the system developed by Joshua with the granular jamming, you are also using vibration, but also together with vibration, you're using the basically compression of the granular jamming, which let's say it's a kind of pressure. So basically, you apply different pressures. And as you presented in the beginning, our sensitive organs in the skin, some of them they're sensitive to pressure, some of them they're sensitive to vibrations and other things. So what's your view on, let's say, in terms of the technology we have available and the kind of stimulation we can provide to the human skin? What is vibration good for? What is the pressure good for? How about, let's say, either using vibrating motors or tactile displays that can provide pressure? What's your take on, let's say, how these different technologies can be used?
Okay, maybe the easiest answer to this will be, if we think about viable products, something which can go into industry to end users, we should think about what is easy to design and integrate into commercial products, other than in research lab. And things like vibration, they are easy. Mm-hmm. That is why smartphones, laptops have them. While, as you mentioned, pressure, anything to deal with pneumatics or hydraulics will not be feasible to implement in a smartphone. So there will be no industry drive for that. But from a research point of view, we can build as many complex systems as we want and test them. And maybe for industry like space or military, that is not a problem.
Mm-hmm. But so, for example, let's say tactile displays that, of course, are more complex because you have to provide actuation on different points. You think at the moment maybe there is no, let's say, a killing application that will make it so adopted by industry, by big industrial players, and so it's not as developed.
Interfaces which have individually controlled actuation pins, something like this, let's say, which directly come to your skin, at the moment are expensive, I would say. There are piezo actuators, but again, they generate vibration. Mm-hmm. And another type, there is electrotactile stimulation. But this is it's not yet invasive, but it's going there. So it's introducing electrical signals to your skin, and based on each individual we can create certain tactile illusions, or we can create pain if we want to. So which is not a killing application.
But another kind of killing.
There is one industry which is probably #1 beneficiary of haptics, which I would not mention here. A lot of soft haptics, rigid haptics, different materials, vibrations are required for physical human-robot interaction, human-machine interaction in that industry.
Yes, I think we had a conference in London about that.
Yes, there is a separate community doing that, and industry. I am not familiar with.
Okay, I don't see any more questions in the chat. So thanks, Ildar. Thanks for your time and for the talk. Very interesting. I like that. Yeah, I mentioned already the multimodal perception, but also you mentioned these illusions. I think in many fields we see how the study of illusions is interesting to understand more how the human brain works, and we actually seen some example also in previous seminars. I think it's a very interesting aspect to observe. And yeah, thanks again. And I close the session now. And thanks for being with us, and thanks everybody for attending the seminar. Bye, everyone.
Thank you.